Okay, so we don't have much time, only half an hour, so we have to rush. But now we're going to look at a posteriori error estimates. So what is an a posteriori? So you know, a priori comes from Latin. You say, well, before, right? A posteriori is after. So before, yeah, we know what we would expect. So if I know the rates, the a posteriori error estimates, then I know what to expect from a finite element solution, right? So then you solve it, and then you know, okay, well, I would expect to have a rate of convergence of 2 if I use quadratic Lagrange elements for solving this problem. That is smooth. That is the whole thing about a priori error estimates. Now, a posteriori, which means afterwards, allows you to actually predict what would be your value of the strain energy, the exact value of your strain energy. So, of course, we're dealing with problems for which most likely we're not going to have an exact solution, but we can still approximate a value of the exact solution by using these estimates. Okay, so how do they work? Well, and we're going to just be dealing with algebraic convergence. But let's put a title on this. So if you remember the estimate that we saw, it was u minus uh less than or equal to c1 h to the beta h, which is our convergence rate, u, right? And you would expect that for very fine mesh, this guy here gets transformed into an equality because these are actually sharp estimates for small h. So what we want is to compute the exact strain energy, right? So we want this is by our definition, right? The error in the energy norm is linked to the strain energy. If you remember the equations that we saw first in 1D, where this big U, right, is our exact strain energy. Yeah, and well, if you remember, U, that is a function of the solution, can be written as 1/2 of the bilinear form applied to U on U, and this norm, then it is equal to the square root of 1/2 of BUU. So now we have basically this guy. Okay. Now we're going to take a look at this other side here, and we're looking at the error. So what we want to do is to transform that norm of U minus UH into some sort of error in strain energy. That's what we want to do, and we're just going to use the same equation. So if we square that term, I'm getting rid of the square roots because the term is a square. So now I have U minus UH, U minus UH, and that is actually equal to BU comma U minus 1/2 of BUH comma UH. And if you look at the notes of the first chapter, there is actually a theorem that proves this there. So the bilinear form applied to the error, is equivalent to that bilinear form applied to U minus the bilinear form applied to your approximate solution. So that it has been proved already. And well, we can claim that all of this here is our, let's say, error in our strain energy, which is basically U minus UH. So I hope it's clear when I'm dealing with big U, like uppercase or lowercase, I'm referring to either the strain energy or the solution. So now that I have that, right? When I look at the equation up, this equation here, I see that I basically have 3 unknowns in that equation for getting u. So how many equations I need to get u? I have 3 unknowns. I need 3 equations, right? So I can get, so let's write that down. Which are my C1, my beta H, and my U. 3 equations. And then we're going to write those 3 equations. So what you do is you actually take 3 different finite element solutions where you're actually decreasing mesh size. And with those 3 solutions, we're going to write these 3 equations. And we're going to try to find or extrapolate what would be the exact strain energy for our problem. So you take the first solution that we are basically going to call, well, the strain energy for that first solution is UH0 is equal to C1 squared. So keep in mind that now I'm squaring everything, so that's why I have this U minus UH0 here to the left. So I have to square the other side as well. So it's H0 to 2 beta H. And then U, this is going to be my first equation. I take the second equation, I do the same, but now everything is related to the second mesh that I'm using. C1 squared and I get my first mesh. Yeah, and that is going to be my third equation. So now I'm going to just play with this because I just want to get rid of the constants. So I'm going to take the log of 1 divided by 2. So I take this equation here, and then I take this equation here. So if I take the log at both sides, you basically get U minus UH0 U minus UH1 is equal to 2 beta H, and then the log of H0 divided by H1. We're going to call this 4. Yeah, and I'm going to do the same with the other 2 equations. So I have 3 equations, I take the first 2, I take the other 2, and then two divided by 3, and that's, you get something similar, but with the other 2 solutions. So U minus UH1 U minus UH2 2 beta H log of H1 divided by H2, and this we're going to call 5. And then what do we do? I have 2 equations left. What can I do with those equations to get rid of the constants? Who has an idea? We divide them, right? If I divide 4 into 5, right, I get rid of the 2 beta H. It's not there anymore, so I get log of U minus UH0 U minus UH1 divided by the log of U minus UH1 divided by U minus UH2. Good. And this is equal to the log of H0 divided by H1 divided by the log of H1 divided by H2, and I'm going to call this Q. It is a relationship that is not going to change. I call it Q. Q is our in a way our constant. right? So if I take that equation, I can actually rewrite this. So if I take, let's say, the first part of the equation, let's take only the left-hand side, and we get the log of u minus u h0 divided by u minus u h1. It is going to be equal to q, the log of u minus u h1 divided by u minus u h2. Or a different way to look at that equation, if you just get rid of the log, that equation is basically saying that u minus u h0 divided by u minus u h1 is equal to u minus u h1 divided by u minus u h2 to the power of q. And that is very interesting because now we have just a single expression where you have the exact value of the strain energy, you have the approximate value of the strain energy of 3 different finite element solutions, and then you have q, right? So what is the problem now? So I have basically u, and u is unknown. This is what I want to get. UH0, UH1, UH2, these are known because are values that I get from my simulations. And I get Q. And what is Q? Well, Q is something that I can determine very simple because I can basically compute that for my finite element mesh sizes that I use for those simulations. And so what you are dealing with now is the solution to a nonlinear equation. So if you compute Q, you compute 3 finite element solutions, then you get 3 values of strain energy, then you bring all of these into nonlinear equation, and you can actually get an approximation of your exact strain energy now. This is super cool stuff. Because most problems don't have an exact solution, but I have a means to get an exact solution, sort of. I have the means to get the value of the strain energy. But the exact strain energy, this is super powerful. Right? Because then when you go to the industry, now they are going to say, well, does that make any sense, what you're showing me? This is just finite elements, a black box, I put loads, boundary conditions. Is it any good? And up until now, the answer to that should be, I really don't know, right? But now you should have a different answer. You can say, well, look, I actually computed 3 different meshes. I computed the value of the strain energy, and I actually did convergence on this without having the exact solution. And that is super cool. Well, for me at least. Yeah, it's super cool stuff. Anyways, so what you do now is that you solve for the exact value of your strain energy. We can solve for u. And since we know that your h is somehow related, I mean not exactly, but it's related to the number of degrees of freedom as 1 over n to the power of 1d, and you can actually test this in your problems. You will see that they are very, very close, where actually d is, again, the dimensionality of your problem. Then you can also apply all of this stuff that we have been discussing, not to h, but to the number of degrees of freedom, because, well, if I just take a look at this expression here, so h0 divided by h1 is actually equal to n1 divided by n0 to the power of 1 over d, and I can do the same for h1 divided by h2 is equal to n2 divided by n1 to the power of 1d, and then I can compute my q as the ratio of the log n1 divided by n0, and this divided by the log of n2 divided by n1. Yeah, and now you compute your q factor. Even if you are not, even if you don't want to work with your h values, but you want to work with degrees of freedom instead, right? You can also compute your Q. So you can also use this with p-FEM. And so what did we do? Very simple. Let's do a recap. We have our algebraic convergence. Yeah. And for that, we said, well, we have three unknowns there. UH is something I know because it's my approximate solution. U is what we don't know, is our exact solution. And then we have these constants. So we have three unknowns. We write three equations. By working a little bit on those three equations, we managed to write a nonlinear equation to find the value of the strain energy, the exact approximate strain energy U. And this is all I have to say about a posteriori error estimates. And if you look at the project, in the first exercise, I asked you to obtain this, right? Yeah. So who has computed already an approximate version of the strain energy? Who has done this? No one? Why? Because first we didn't have a theory, now we do. Second, well, we're solving a nonlinear equation there, so that is actually not so easy to do. But who can tell me how you can solve this equation? Who has looked at the brightspace in detail? No one. Okay, if you go to the resources of the brightspace course, there are two files, right? One is a finite element package that you downloaded, so all of you should have seen this already. And the other file is something that a posteriori.py that actually you can use to compute this value, because it is not trivial to do. Okay, it's just a solution of a nonlinear equation, and there are many ways to do it, and some ways are not so nice. Okay, so you just, for the project, just use the posteriori.py I provided you with in the brightspace. Okay, but now there is one last thing I want to discuss today, and we still have 15 minutes, correct? Yeah. Otherwise, we're not gonna make it. We have some time, so that's why I'm rushing, because I really want to finish. Next class, I want to do p-FEM in 2D. So this is something I think an important ingredient for you to test your formulation. So we're gonna look at what we already said a little bit: high order patch tests. Okay, we discussed a little bit about this already. You have a formulation that you want to test. Let's say your h-FEM is perfect. It works nicely for h-FEM, for let's say smooth problems. You get energy error in the order of 1. So that is your rate of convergence. So everything is going very nicely. Now you go to p-FEM, and the first thing you did is, you implemented your quadratic shape functions, and you want to see whether your formulation makes sense. So we said, well, one way to do that is just solve a quadratic problem, and then if you get a 0 error, that means that your formulation is correct. And so that's where these high-order patch tests come into play, because the idea is to construct a solution that you can actually use to test whether your formulation is working properly or not. Okay? So we looked at what was the patch test? Who can remember we had this discussion on the patch test? What was the patch test? It was a test created by a guy named Irons many years ago that tested what? No one remembers? No? So the idea was, well, back in the day, people were creating new elements for the finite element method. In fact, there were some people who got their PhD just by creating new finite elements. So they needed to test these elements, right? Because it's not just to create a new element. You had to prove that it actually worked with the method. And so one way is to create a patch test that basically is a very simple problem that it really puts the element to test. So you put the element in a very weird shape, and then what you're trying to do is to try to recover whether that element can recover a constant state of stress or strain. Because if it does that, this is a necessary condition for convergence. If your element, as you refine your mesh, right, does not exhibit a constant state of strain or stress, then of course you're not going to get convergence. Your solution is going to be blowing up. So that is the whole thing behind the patch test. And in fact, in your program, you have a patch test, right? The second example I gave, well, we're going to draw it here, but that is a patch test. So if you remember, we did something very simple. We had some sort of mesh that looked like this, and inside we just placed an element so these are quads, and then we said, well, I want to place a uniform load on that edge, and I constrain that test and if I can recover a constant state of strain, that means that so if my solution is linear, in this case the solution is linear, then my stress is constant. But when we're testing high order formulation, of course I'm not interested anymore in a constant state of stress, right? I'm interested if I do a p-FEM and I'm testing p equals 2, what is the order of my stress? Come on, guys. P equals 2. My solution is p equals 2. How do I get the stress? Linear. Yeah, you just apply the derivative, you obtain the strain, and that you multiply with your constitutive tensor, and then you get stress, so your stress should be linear. Right? So, for high order approximations, what we do is we're going to create a problem such that the exact solution u of x belongs to some space. If you remember, we call this space of polynomial interpolation orders on omega. And then what we are going to do we're going to decide of an exact solution, right? We choose ourselves our exact solution, and then we come up with the problem. So in the case of elasticity, if you remember, we were dealing with the divergence of the stress tensor plus b is equal to 0. Then basically all I have to do is to apply what is that exact solution. So I obtain the divergence of that stress that is a function of my exact solution, and I obtain some value or some vector valued function which is my body force, and I call it F just to make sure that I don't confuse that with the body force. It's not a body force, it's a pseudo body force. So by choosing your solution, basically what you're doing is, okay, what would be the body force that I have to include in my approximation to solve my problem to get me that solution back. Okay, so when you do that, then you solve. For my right, and keep in mind that now I am solving for my approximate solution, right? So this is not anymore. This is actually where I am going into my program and I'm getting, okay, I'm gonna test a polynomial of order 2. This is now my approximate solution, right? And I'm using that pseudo body force. And if everything went well, and let's say my exact solution that I took was a second order, and now I am using for my approximate solution a second order, I should get 0 error. Yeah, of course with boundary conditions, otherwise you cannot solve this. And t is equal to right on gamma t, and keep in mind that of course the boundary conditions have to reflect the fact that I'm solving that particular problem. So the tractions have to come from taking into account the exact solution that you chose, right? And the same thing with u is equal to u bar on gamma u. So these three ingredients in the end define your boundary value problem. You can obtain your UH, and this is the way you can test for higher order approximations. So when you go to your p-FEM, right, first thing you do is you try to model a square problem. How many elements you need to model a square problem? 4. Another guess? 1. You need only 1. Why? One is the simplest element that can give you a quadratic solution if you have a quadratic problem, because you have an internal degree of freedom that describes the quadratic behavior. So now that everything is fine and you work your formulation, and with one element it's working, your implementation is working, what is the next level of complexity? What do you do next? Who can tell me? Or what will you do? Let's say now it's working for one element. Then what would I like to see? That the code is robust. So what will you test next? Huh? More elements. So you take 2, and then by taking 2, you're already checking other parts of your program or your final element software. Now you're checking the assembly, right? If the assembly is working properly, because when you are basically dealing with p equals 2, you have your first element with certain degrees of freedom. It's going to have 3 degrees of freedom, right? And those are going to be located somewhere in your global stiffness matrix. And then for your second element, it's going to have another set of degrees of freedom. So by taking 2 elements, you're already testing the assembly part. You guys get that? Yeah? So then what would be the next level of complexity? Now we have 1 element is working and 2 elements is working. Then what? How many elements we take? You don't really need to, because if you test the 2, most likely it's going to work for anything, but you test anyways, right? You test for more elements. And once you're done with more elements, at least you know that for p equals 2, your stuff is working. And then you change properties, and then you see, well, I was doing p-FEM, but my area was equal to 1, and modulus of elasticity is equal to 1. So now I change those properties, and I keep testing. And if I get everything is working perfectly, what would be then the next level of complexity? So now P2 is finalized. I get the right rate. How much is the rate for P equals 2? HFEM. HFEM rate. 2. Say 2. Very nice. So now we get our convergence rate equals to 2. Then what do? Are we done? You bet you would be done. Then you need to get the project right. And to get the project right, then you need to go for higher P. So then you need to take what? P equals 3, and what do you do for P equals 3? What problem you solve? You kill me. No. We're still working about everything in 1D, okay? But what do you do next? Now your stuff is working with p equals 1 and p equals 2, and now you want to test it for p equals 3. What do you do? Your quadratic elements are working. We're done with p equals 2. It's working for p equals 1, and it's working for p equals 2. Now I want to test p equals 3. So what do we do? Huh? What do we do with the cubic? So, okay, guys. If my stuff is working for p equals 2, right, and I solve a problem of polynomial order equals to 2, the error should be what? 0. So, if the error is 0, can I test for convergence rates? No. Therefore, right, to test for the convergence rate, one way is to model a more complex problem. And then you get your nice beta h equals 2, right? But now we're going to the next level of complexity, which is I want to get my code working for p equals 3. So what do? You model what? One element. But what is your exact solution that you assume? You're going to manufacture a solution the way we just did it here. And what type of solution we want to manufacture?
Quadratics.
No. Cubic. We want a cubic, right? Because our quadratic formulation is working. So if I come up with another quadratic problem, of course it's going to work, right? Now we go to a cubic solution for which we do all this trickery here, and then we obtained, I assume, a cubic polynomial, right? And then, well, I compute what would be the value of the pseudo force that I need to apply for my problem. And now I assume for my problem a polynomial order of order what? For my approximate solution? 3. Now, what would be the error? If everything went well, it should be 0. And this is the way you build up your software and the way you basically test. So you start from very basic and you move forward from that point. Right? This is the way we do stuff in computational mechanics. We always start slow, small, and then those are building blocks, and then you keep building on top of that. Okay? All right. I think that's it. We are running out of time. Any questions to finish the lecture? No. Excellent. I will see you next Thursday is the last class. We're going to look at p-FEM in 2D. And I'm gonna do this whole doodle thing so that we find a better time spot for the office hours.